Hello, everyone. Welcome to today's VELOVirtual webinar, where we're going to talk about how to build a better fuel tank fast. We're going to talk about legacy manufacturing and the challenges therein, what new shortcuts we can make with metal AM, and also what differentiates Velo support-free technology from typical laser powder bed fusion systems, and what are the advantages with Velo. So we're talking about pressure tanks, pressure vessels and tanks. These are commonly found on high value vehicles like rockets and satellites, where there are some seriously precise acceptance criteria for designing a proper part for the application that's needed. Some of these constraints are, as you see here, the weight of the part really needs to be minimized on these high value vehicles. The heavier your vehicle is, the more expensive and laborious it would be to put it to its final destination. Pressure optimization for strength of the application is another main goal, and something that additive manufacturing really helps to capture and is optimized even further with Velo3D's support-free technology. The size of the part is very important to conform into these tight spaces and tight packaging. The smaller the vehicle is, the more effective and more ideal it would be. So oftentimes these parts have to fit inside some very complex componentry, and having that design freedom is very important. As well as being able to pivot and change design rapidly without pushing out your lead time. Oftentimes changes need to be made in the design process, and if that pushes out your lead time excessively, then that is a big detriment to the entire project. Our main goal is to be able to pivot and change designs without pushing out the overall lead time, such that we can iterate rapidly without causing a detriment to the delivery date. So what are the challenges with 3D printing of these specific pressure vessels? First and foremost, you have low angles. And printing of low angles, we all know, is Velo's claim to fame. It's what we do best. And inside these enclosures, if you add support material, you can't really get it out. Oftentimes it's extremely difficult or nearly impossible to get out this added support material. And it's a catch-22 on an incumbent metal 3D printer. For these low angles, you need to add support material, but you can't get it out. Velo3D just doesn't need to add support material on the inside of this part, so it's printed completely support-free. As well as the high aspect ratio of these parts, as you print thinner and taller sidewalls of these parts, you run the risk of recoder interference or deformation. It's another thing that Velo3D just doesn't have to worry about. Our recoder does not come in contact with the part at any time during the print, so we don't have to worry about things about orientation to the direction of recoat. Another good advantage is these ISO grids that we see commonly on these pressure vessels. As you see here, yes, they're Velo logos, but it's designed to exemplify an ISO grid that is added for structural rigidity to the part. And we can print these protruding features without having process breakdowns or increased surface roughness. Oftentimes that could be a detriment to the overall integrity of the part by causing stress concentrations or crack initiation sites on the outside walls. So a typical metal 3D printer would look at this and say, hey, I need to add a bunch of support in here. Everything that you're looking at here is below 45 degrees, colored in blue, all the way down to a red. These high aspect ratios as well are challenging for an incumbent to print. The taller you go, like I said before, the higher the risk of deformation or effects of the direction of recoating becomes further challenging. This is something that is straightforward and easy for Velo Sapphire to print. It's something that we pride ourselves in, and in this case, we don't have to get inside the part and remove any of these necessary support material that an incumbent would have to add. So this is another example of what Velo3D is doing to redefine what is manufacturable. Our goal is to really expand the design space of what can be actually manufactured from the true design intent of the engineer. So enabling manufacturing without the design for manufacturability is a big goal. Comparing legacy manufacturing where you would need maybe skilled labor like welding process, or you would need to design tooling for perhaps a casting process, the lead time could be in the matter of quarters or longer. Additive manufacturing cuts that corner a good bit by reducing the amount of skilled labor or the need for tooling design. However, there's still the need for support removal and possibly some laborious post-processing that needs to be done to the part. Velo3D further cuts that corner by reducing the amount of difficult to remove support and cuts it down into a matter of weeks turnaround time from design to manufactured part. This is all made possible by the Velo3D platform. It's a one-stop shop. We do it all from start to finish. It begins in our flow print preparation software, where we would orient the part in 3D space, add support material where necessary, and then actually prepare a print file that's then taken to the Sapphire Metal 3D printer for printing. Through that entire process, all of the sensors and metrics are monitored by our Assure quality validation software. And the Assure software provides a end of build report that will accompany every part that's printed on a Velo Sapphire. This is a direct representation of all the sensors in the machine, such as powder level, such as humidity, powder bed quality, even any interruption is reported in this build report. So expect to have this qualitative and quantitative report to accompany every part that comes off of a Velo3D Sapphire system. So SupportFree is something that, is it gets tossed around, and, to really explain what it is, we've really learned that the big problem is printing a complex part. And that big problem is much easier when we break it down into smaller problems and deal with them on a problem by problem basis. And that's what the flow software does. It recognizes these specific features and applies specialized laser parameters to each type of geometry in order to print them successfully without a process breakdown or without the need for support. These types of features are bulk areas, peninsulas, low overhanging features like vertical walls, closures, especially low overhangs, are all automatically recognized by the flow software and apply specific laser parameters. On the right-hand side, you see an existing laser powder bed fusion system and how they struggle with low overhangs. The typical rule is 45 degrees before you see any breakdown or degradation in the process. Even at 40 degrees, you can see an increase in surface roughness, but then at 25 degrees and below, you have serious problems with resolving any type of geometric feature. Velo3D Sapphire just doesn't have this problem. We can go as low as 10 degrees, even lower in some cases, like I'll talk about in the next slides. But you see there's no degradation to the surface roughness, and it's very predictable, and it's an engineered surface. It's designed to be this way. And it's something that sets us apart from other incumbent metal AM features. Our material properties are better than cast, we like to say. In some cases, we approach metal properties of forged or wrought materials. The density is 99.9% right out of the printer. Our geometric accuracy of small features is plus or minus 50 microns. And on larger dimensions, we expect to hit between plus or minus 0.2% of that nominal dimension. All of our material properties can be found on our website. Getting into specifics as far as dimensional limits, horizontal holes are something that we can print a maximum ID of 100 millimeters. This is something that is pretty straightforward and reliable for us to print. The minimum that we can resolve and still maintain a flowable passageway would be 500 microns. we take that same hole and tilt it, then our maximum ID increases greatly, by far beyond 100 millimeters. We're almost more limited by the diameter of the build plate than we are of the diameter of the hole if we tilt 10 degrees or more. Again, the same limitation for minimum ID, however, is 500 microns. Dome closures, another really advantageous orientation and shape for us to build. We can build features unsupported well over 100 millimeters. Again, we're more limited by the size of the current build plate, which is 315 millimeters. But this is something that we really leverage this type of shape in order to print an unsupported dome closure. Horizontal spans, we can easily close a 10 millimeter gap. The minimum width between those two walls would be 250 microns before the walls start to fuse together, actually. So using these angle guidelines and these shapes in this practical application of the pressure vessel, we have two main shapes. There's an outward growing cone at the bottom of the part and an inward growing cone at the top. And I'll elaborate a bit more on these moving forward. However, at the top, this inward growing conical surface can be printed unsupported without process breakdowns. And at the end of the day, it's just a much friendlier end result. You don't have supports on the inside to remove. So this is to simulate the build. We start with the outward growing cone. You can see there is some support material. That's supported up to about 30 degrees, and that's printed without any process breakdowns, but those supports will be removed after the part is removed from the build plate. Then moving up on the outer wall is the higher aspect ratios that can sometimes be a challenge for a typical laser powder bed fusion system that has a conventional recoder that contacts the part each layer. Also is the ISO grids that you see on the outside that are printed without process breakdowns, and really enhances the structural rigidity of the part as long as it prints as it should without added surface roughness or process breakdowns. Then the toughest part of the pressure vessel to print, that's the top closure. That closes out completely support free. There is powder on the inside, but it's a quick turn it upside down and tap method that you can get all the powder out. And at the end of the day, there's no reason for you to do any post-processing on the interior of this part. So really, I mean, a direct comparison of what a conventional AM printer would have to support. Everything you see here is supported up to 45 degrees on the inside. I for the life of me, don't know how you would get these supports out. It just doesn't pose a really possible way to print a part. The Velo3D support-free system is completely free of supports, and it's kind of a no-brainer. I mean, which would you rather have at the end of the day? So really pushing the boundaries of what parts are manufacturable are some examples of success stories that we've had. And this is another one that we can add to the list. Looking at our Sierra turbines, this is a gas microturbine that we printed for Sierra turbines. A lot of improvements for power density and improvement in durability. But really, I think one of the biggest advantages here is the ability to consolidate 61 parts into one and really have a dramatic weight savings at the end of the day. The cross section there shows a conventional AM versus Velo3D. We really like to use this to show how, just not possible this part would be to print on a conventional AM and have a useful part at the end of the day. The Hanoi Supercritical CO2 Systems Impeller is another success story we had. This was an accelerated development time which required no redesign from the manufacturer, or I'm sorry, the designer. This is something that we printed at a contract manufacturer site. This was actually printed at Stratasys Direct Manufacturing. And again, the cross section showing the difference between conventional AM and Velo3D support-free technology. So what are the real benefits here? What is the real nitty-gritty of printing on a Velo3D Sapphire system here? We turn the part around, you'll have a finished complete part in a matter of weeks. We can reduce the part count to tens or hundreds, so it makes sense to print in smaller batches, and we can really reduce the weight, especially with the high aspect ratio challenges. We can really go to thinner wall thicknesses without the concern of interference due to recoating. This is a close-up of the ISO grid that we have on the outside. This printed free of support. It's not post-processed. This is to simulate the ISO grid pattern that you would put on the outside or inside of these parts for enhanced structural rigidity. Really, the difference here is that it's a smooth surface. There's no stress concentrations and no process breakdowns. So you don't have these manufacturing defects that cause stress concentrations or crack initiation sites. This really helps the overall life of the part and the endurance of the part at the end of the day. Another advantage is how we blend these processes together. You can see the top facing surface. There's no tessellations from mesh. There's no step lines where the process is abruptly changes. This is another stress reduction technique that we use and like to highlight here, that you can expect your part to print as the design is intended without cause for compromise or disappointment when you see your part at the end of the day. This is something we haven't actually cut this apart yet, and we will be posting images on our Velo3D blog, as well as quantification of the surface roughness that we get on the low angle closure. So expect more to come on that, and we will be posting that on our blog. So this time I'll take the floor for any questions. Mike, do you have anything that you'd like to send my way?
Yeah, we have a couple. One, I think just to maybe for context, what metal was the part printed in? I'm not sure if you mentioned that.
Oh, no, I didn't actually. This is a titanium, a Ti-64 alloy. This is a typical material that we have printed for a few customers thus far for high strength, low weight type of material for actually a space flight application.
And what metals do we print in general?
In general, so Inconel 718 is probably our most widespread material. We also have aluminum F357. Inconel 625 is in the pipeline, and we have Hastex and C22 capabilities.
How tall is the part? I know there was a slide there that had like 315 millimeters, but give us a scale maybe?
So it's about 13 inches tall, a little over a foot tall. We could print taller than that. The maximum capability of the current Velo Sapphire is 400 millimeters. So we could go a little bit taller than that.
Okay. Let's see here. What kind of recoater do we use on the Sapphire?
So that is our proprietary bread and butter recoater. It's different than anyone on the market. It's really what the company was founded upon. We use a method of sprinkling down a layer of powder on top of the part, and then we actually normalize that surface with a blade. However, that doesn't come in contact with the part because we remove a good portion of material. Actually, all but 50 microns of powder is removed each layer. So the blade never actually contacts the part. It's a revolutionary proprietary recoater.
And what is the step height per layer?
It's a 50 micron layer step height, and it's also something that each process is catered to do. We do 50 microns, and that's it. There's no 25, there's no 10. We don't play with that number at all. It's all 50 microns.
And I know you kind of mentioned that you'd have some information on the blog coming up soon. But what's a typical downskin surface roughness for, let's say, 20 degrees for the supportless overhangs?
So that's something we didn't have a slide specifically on surface roughness, and I can get into that more graphically. However, you can expect surface roughness to be under probably around 10 micron SA at a 20 degree overhang as far as a typical surface roughness that you'd find at about that overhang.
Okay. And what are the typical post-process treatments that you would do on Ti-6-4?
So Ti-6-4, it prints very hard. It actually prints pretty brittle and isn't a good engineering material to use right out of the printer. So it needs a secondary heat treatment to reduce stress, as well as normalize the microstructures so that you have some ductility in the material. So you would need to first remove all the powder from the inside of the part. Then you would do a stress relief in either an argon purge or a vacuum furnace, and then remove that part from the build plate. After that, you would have more specifics as far as post machining, or a more specific heat treatment that you would need to apply in order to get your desired material properties. So after stress relief and removal from the build plate, then it becomes more application or part specific.
And is there, how does the part behave after heat treatment? For example, is there any distortion?
No, not typically. The first stress relief that we perform is designed to normalize internal stresses and avoid primarily cracking when removing from the build plate, as well as part deformation, so that you, after you remove from the build plate, you have as close to nominal dimensions as possible.
This one's an interesting one. I'm not sure we've had this one before, but what's the minimum hole size for efficient powder removal?
That is an excellent question. So I'll typical engineering answer, it depends. I would say at least give yourself 1 millimeter in any case. That's as small as you could possibly go and really get anything out. But that being said, that's a very difficult hole to get at, and you can't really tap out of that. You'd have to use like a compressed air or a forced fluid in there to get the powder out in some cases. The real answer is make it as big as you possibly can in order to get it out easily. Because the last thing you want is to print a part where you can't get the powder out. It's not only a problem, it's an embarrassing problem. It's usually an oversight. But the bigger you make your powder relief holes, the better. But if you really get into a jam and need to push it down, you could go pretty small. I wouldn't go smaller than 1 millimeter in any case ever, though.
Okay, so to get powder out around 1 millimeter is about as small as it'll go?
Yeah, and take that with a grain of salt. It's going to be difficult, but it is possible.
Okay. Do we monitor thermal history or any, I guess we'll leave it at that. Do we monitor thermal history?
So yes, right now we're in the process of quantifying that and bringing that into our Assure quality software. And what we do is we actually have a photodiode looking at the melt pool of these processes and gathering thermal data. So all of that is processed and recorded, and we are looking towards recognizing process breakdowns or potential defects from this thermal signature that comes off of the melt pool in situ while printing. We do not actively modulate the laser power. However, it is just a one-way gathering of data and information that's used for reporting after the print.
Here's a question regarding Z height. Is the Z height of the build dependent on the plate thickness? Like, do we lose Z height if there's a thicker plate, for example?
Yes, that's correct. So there is a maximum stroke of the cylinder or the build plate inside the machine. The thicker that you put a build plate in, the shorter in height you can print, which is why we advertise 400 millimeter build height. It can be more than that if you are able to put in a thinner build plate. However, the caveat there is that usually bigger, thicker, chunkier parts require a thicker build plate. So it would have to, again, depend on the application, depend on the part, but it is possible to get a little bit extra height with a little bit thinner build plate.
So the 400 that's advertised is based on the thicker build plate?
Yes, that is based on a 1-inch thick build plate. We say 25 millimeter build plate, or I'm sorry, 50 millimeter build plate is a 2-inch build plate.
Okay. Is the remaining powder inside the build chamber loose, or is it centered because of the printing process?
Oh, it's all loose. We only fuse what we want to make into solid material. Everything else is easily vacuumed up at the end of a print. So the print would complete, and inside the chamber, below the build plane, is your part sitting in a bunch of loose powder. There is a vacuum wand that the operator would then activate and vacuum out all of the loose powder. It's brought back down under argon purged environment to our hopper reservoirs, and then ready to be reused on the next print. The only other powder that would be need to be removed in this case would be the powder that's inside the pressure vessel, but that's all loose and able to be removed just either through gravity, or you could use compressed air. We don't like to use compressed air on titanium or aluminum, but you could use a purged, like a glove box, to use compressed air or compressed argon in that case to remove powder from internal channels and passages, and in this case, the pressure vessel.
Okay. What's the build envelope of the Sapphire?
So the current Sapphire that we have available on the market is 315 millimeter diameter round build plate by 400 millimeters tall. Again, that's a little bit variable based on the thickness of the build plate that you want to put in. We also have being available in the next few months is a 1 meter Z system. So that's 315 millimeter diameter by 1,000 millimeters tall. Coming soon, next year will be the Velo Sapphire XC, and that's a much larger build platform. That's 600 millimeters by 550 tall.
Okay. Well, here's some interesting questions. So what simulation software do we use? And I guess I'll open that up to any other preprint software suites.
So like I said in the one slide, we're a one-stop shop. We do everything that we need for our manufacturing process is all proprietary and designed by us. There are some other third-party softwares that you can use, like ANSYS is one, for example, that you could do a stress simulation on your part to kind of help you move forward and determine where your stress concentrations are going to be or where deformations might occur. However, we don't actively have one readily available for that at this particular moment. We are working on some distortion simulation softwares. However, it's not going to be available. It's not in the readily available pipeline. Maybe years down the road we'll do a deformation software suite. But right now the software is print preparation, where we would determine a print orientation. We would add support actively in the flow software, and then the actual preparation of the print file where the specific laser parameters are applied. That is the only type of software, preprint software, that we use actively for a typical pipeline production.
All right. Do we use any platform preheating or chamber preheating?
No, we don't actually. It's been designed in as a possibility if we ever found the need to do that. However, we have some proprietary processes, especially for titanium, that drives the cooling rate slower than a typical incumbent powder bed fusion system. So we can actually, it's not a stress relief to avoid deformation. However, we can reduce the likelihood of cracking of parts. And that was the main concern with a heated chamber. If we would need to heat the chamber in order to slow the cooling rate of the material to avoid cracking. But we found other ways to avoid cracking through laser processes specifically that enabled us to print large, chunky titanium parts without cracking.
And for any of the other metals, is there preheat used for any of the other metals?
No, we didn't find that it was necessary for any of our other alloys as well. So as they sit, there's no heating of the build chamber at all. That being said, it's a laser. It's a kilowatt laser. It gets a little warm, so it does heat itself through the process. However, we aren't actively heating the elevator or the build chamber or anything like that.
We have two of our favorite question, and I'll open this one up. So supports are intended not only for keeping geometry, but also for conducting heat. How do we deal with the latent heat reduction if we're printing support-free?
That's a great question. And there are limitations to this, and it is a challenge that we have catered our laser process to overcome. Specifically, the one slide I have shows peninsulas. Peninsulas are challenging because they're a low overhang, but very thin. And those are great spots for heat to accumulate, and you get over melting and process breakdowns. What the peninsula process does is actually reduce the laser power so that we avoid the overheating of these low overhangs. And even on a typical low overhang, a larger feature, it does, the laser power is specifically catered to avoid overheating of these low overhangs. So yes, it is a challenge, but it is something that we have catered our process to overcome.
And is that kind of a sneak peek into how the platform does support-free? There's another question in here that mentioned the recoder, but are there any other technologies being used to print support-free?
So without getting into like any IP or specifics as to what we're doing, I can say we're doing something very unique and revolutionary. And it's not something that, you know, we want to be very open and say that we are doing specific laser parameters on these specific geometries, but I can't get into any deeper specifics than that. I can't get into laser powers or hatches or laser movements or anything like that. That's all proprietary, unfortunately.
But it sounds like the answer to this is somewhere in the parameter sets that are being used.
Yes, it's in the IP that I can't disclose here.
Okay, excellent. Is the Sapphire system open in terms of materials, or how does somebody bring new materials into the Sapphire platform?
So we do our own internal process development and then deliver that to the customer. Customer that would purchase a machine, especially a machine of a material that we have not developed yet, we would, in parallel with building the machine for that customer, do process development and deliver them a recipe that they would use to then print in that material. And it's something that we do quickly enough that does not push out the lead time of the delivery of the system. Like I said, it's done in parallel, and we can do it in a matter of time that is aligned with the hardware production.
There's someone who is asking a little bit more information, or can you repeat how the contactless, he calls it impeller blade, but how does the contactless recoder process work?
Okay, so again, I can't get too deep into the IP of it, but in a nutshell, it is we lay down a layer of powder. Now that layer of powder is thicker than we want at the end of the however, that's sprinkled down evenly and uniformly across the powder bed. Then a blade does come and normalize that surface, so makes it flat. However, that is still above the part. It's not touching the part. That blade is only designed to make a nice flat powder bed. Then there's our proprietary process that comes and removes all but 50 microns of powder. And that's what is the layer of powder that's then, the laser is then applied to. And that's something that we have a structured light scanner built into the printer that's monitoring the quality of the powder bed with each layer. So we can do it uniformly, we can do it repeatedly, and it is quantified. Like I said, at the end of the build, the Assure software will give you a report to really quantify the quality of the powder bed throughout every layer of the build.
A well crafted answer there to get around the IP issues. Good job. Can we select print parameters to get specific microstructure, grain size, or strength properties?
So our main goal thus far has been to print fully dense material. I know that it is possible. However, it hasn't been our main area of focus to really drive microstructure, grain size, grain shape. Our main goal has been to print fully dense material, and whatever microstructure or material properties would then be driven by post-processing heat treatments. It could be possible. However, it hasn't been our main focus thus far.
If a higher surface quality than as printed is required for the internal structures, what would be the post-processing technique that one would use?
So there's several different processes that you could use in order to get a better surface finish or a more polished surface finish on internal features than as printed. Extrude hone is one that's typically used, and it's like an abrasive slurry that you blast through the inside and internal passages of this part, and the small little particulate ceramics or media smooth away and polish the internal channels. Another one is vapor honing. That's another one that's it's an abrasive powder that's blasted through parts and designed to polish internal features. There's several that you can use, but extrude hone is probably the most commonly used.
But you showed a part earlier that I think was a Hanoi Impeller. Do you know what process they used for that? Just as a reference point.
So that one is a machine process on the outside. I don't think that they used an extrude hone for that image. But before final application, I think extrude hone was the process that they used.
Okay. Is it possible to print different parts at the same time, or do you have to print the same part? Like it says simultaneously, but can you print different parts at the same time?
Yeah, sure. Like you saw in this print, we printed two pressure vessels side by side. The thought being that we would use one for testing and one to cut open and actually see the internal features of this part. I could have put any part I wanted to in there as long as it fits inside the build volume. The Flow software is capable of printing multiple parts with different geometries throughout any type of build, as long as it fits geometrically inside the build volume.
Okay. Can we repeat how thin we can get the walls and printing reliably?
So as far as, like a local small thin wall, we can go as small as probably, 100, 120 microns. However, then that opens up new challenges. The thin walls, if they need to be leak tight, we like to go a little bit thicker than that, probably 300, 350 microns for minimum leak tight reliability. And then if you're printing a very, very large thin wall, then, internal stresses of the part start to play a role in deformations during printing. It's not the recoder that's actually contacting the part. However, it is, internal stresses can cause deformations. So in that case, we would have to look at constraining the walls with an ISO grid like we did here to avoid internal stress related deformations. But long and short, the answer, we can print 100 micron thin wall, but it does come with challenges.
Awesome. Are there any anisotropic issues due to the AM process that they should be aware of?
Yes. So typically we see, if we pull a tensile bar that's printed vertically versus horizontally, there is some anisotropy where a vertically built bar will fail a bit sooner than a horizontal bar. However, everything that we print in a vertical direction is still within spec. I believe our mechanical properties spec is ASTM E8. And even in the vertical direction, we're still within that spec.
Got a couple questions over here. The feature identification process that you mentioned, lattices, and we're growing, outward going, is this automatic, or does someone have to go in and manually do that in Flow?
So 99% of it's automatic. You do have the option to do a manual override for some specific types of processes. Say you're printing a part that you just want to print fast and you don't care about the surface finish on the walls. You can apply, we call it a fast process, that just prints bulk core material right up to the edge of the part so that you don't waste time printing contours. There are also capabilities of small internal holes that we would apply a miniature process on. That's how we can resolve a 500 micron thin tube. And there are some manual overrides, but for the most part, everything is automatic and recognized. Like thin walls, closures, low angle surfaces, those are all automatic in the Flow software.
Are we able to print refractory metals?
You know, not currently. We don't have any refractory metals that we're printing today. But if it's able to be melted with a laser and it's weldable, we would be open to that option if the business case presented itself.
All right, thank you. Here's one more. If the vacuum puts the powder back into the hopper, does it get sieved during the vacuuming process?
Yes. So the vacuum wand or even the recoder is tied into the same system. The vacuum wand will remove powder from the build chamber at the end of the print and deliver it back to the sieve. The sieve is an ultrasonic transducer that then vibrates the powder through the sieve, which is a typical laser powder bed fusion mesh size. And then it is delivered into the hoppers where the powder is stored until the next print. And it's always under an argon atmosphere, never seeing humidity or oxygen.
During the process, is it possible to pause and check and restart?
So yes, you can pause at any layer you want. I don't know why you'd want to check anything, but typically the best case for a successful print is to print uninterrupted. So pausing is something that we do sometimes if we're doing a test build or a process development build. But yes, you can pause. The user or operator has the power to pause a build at any time and then resume the build. Depending on how long the pause was, if you have a longer pause, there is a procedure to follow to have a proper resume of the print so that you don't induce problems like lack of fusion porosity or too thick of a layer. But that's something that we try to avoid usually.
Do you monitor and report spatter levels per layer and throughout the build?
So the spatter is something that is visible. It's more, I think aluminum is probably the more prone material to spatter. It's something that is recognized and quantified through the height mapper, our structured light scanner, and can be reported on a layer by layer basis.
There's one here. I'm not sure if I know the answer to this one. So this would be interesting. What is the resolution of the structured light scanner that you referred to that scans the powder bed?
I'm not sure I can get into that specifically. It's something that, to be honest, I don't know off the top of my head. So I'd be reluctant to give an answer. And moreover, I don't know it's something that we're able to disclose that might be protected by IP.
Yeah, I haven't heard us mention that publicly, so I'm probably with you on that one. Let's see here. There are a couple questions that are, I guess, application specific. So if you have something that's application specific, what I'd recommend is reaching out to info@velo3d.com. Specific things around quoting or anything like that would be the same channel because that would depend on the part application that you're looking for. So I won't bring those up. But I think we've pretty much gotten through everything, and we're definitely ran through plenty of questions here. So thank you, Gene, for running a little bit over on questions, but it was really insightful. And I just want to make sure we get to as many of these questions as we can to answer as much as we can publicly when it's possible. Any closing remarks?
I am enthusiastic with how many questions we had. Actually, it's really good to hear these questions. And like Mike said, please, if you have further questions, especially application-specific questions, we're all ears. We want to hear them, and we want to help you work through your problems. I think problems are something that we really enjoy hearing, and we're ready to tackle any problem you might have. So please reach out. It's good to hear.
And if there are sessions that you want to hear more about, if you want to see or recommend a VELOVirtual session, please feel free to send those recommendations also to info@velo3.com. We'd love to look into it and put together a session for you. We're open to doing that. So hope everyone enjoyed the session, and thank you for joining us today on an interesting day for U.S. politics. You can give your browser refresh button a pause and come in and learn something about the technology that we're doing here. But now you can go and hit refresh again and keep up to date on that. So thank you very much for joining us, and we'll see you next month. Actually, we'll see you next week at Formnext. Stand corrected.